Having established the relation between the flux across a region, specifically a closed loop in two-dimensional plane, and the divergence of the flow, let's now look at the relation between curl and what is called the circulation. So let's recall what we've done in the previous video, and I put a link to the previous video in case you haven't had a chance to see it. We looked at flow in a two-dimensional plane, and we considered a infinitesimal rectangular loop which we have placed in that flow. Now, this is an abstract loop, but you could also consider maybe constructing such a loop with threads and visualize it for yourself, what happens for fluid flows, which you can create on a two-dimensional plane, for instance, on the floor. So let's say we make this loop centered at the point x comma y in the two-dimensional plane. So that's our coordinate system. And the infinitesimal lengths of each of the sides of this rectangular loop are del x and del y. And in the previous video, we considered a flow which had vector fields, a two-dimensional vector field, which looked something like this. So along this segment, we have a vector which looks like it's coming inside of this region. Likewise, we have a vector which goes like this on the segment which is at the top. We have a vector field which looks like this, and then we have a vector field which looks like this. And for a recap of this, again, I'll put a link so that you're familiar with the notation and what we mean by these vector fields and why are we drawing just one representative vector field at the midpoints of each of these segments. It'll become clear if you have a look at the previous video. So in the previous video, we looked at the normal components of this vector field. And with that, we were able to identify that the flux density across this region is equal to the divergence of the vector field. Now, in this video, let's look at the tangential components of the vector fields and see what that leads to. So as before, let's say our vector field is V, and just sort of as a visualization tool, it helps to keep in mind that we can think of this vector field as the velocity field of a fluid in two dimensions. So it has two components, Pi plus Qj, where P is the component of the velocity field along the x direction, and Q is the component of the velocity field in the y direction. Now, as the velocity field varies in space, the magnitude and direction of this velocity field at the midpoints of these segments would be different, right? And we quantified this difference in velocity field by labeling each of these points. So for instance, if the rectangular loop is constructed with x comma y as the center, then the midpoint of this segment, which we call segment 1, that's this vertical segment, the midpoint of this vertical segment would be at x plus del x by 2 comma y. The midpoint of this segment, which we called segment 2, would be at x comma y plus del y by 2. The midpoint of segment 3 will be at x minus del x by 2 comma y. And the midpoint of segment 4 would be at x comma y minus del y by 2. The velocity field at the midpoints of each of these segments. So for instance, the velocity field at the midpoint of segment 1, we can write as P x plus del x by 2 comma y along the x direction plus Q x plus del x by 2 comma y along the j direction. The velocity field along segment 2, or rather at the midpoint of segment 2, would be P x comma y plus del y by 2 along the x direction plus Q x comma y plus del y by 2 along the j direction. The velocity field along segment 3 would be P x minus del x by 2 comma y along the I direction plus Q x minus del x by 2 comma y along the j direction. And the velocity field at the midpoint of segment 4 would be P x comma y minus del y by 2 along I plus Q x comma y minus del y by 2 along j. Now, in order to extract the tangential component of the velocity along each of these segments, we can, just like we did for the normal component, we can take the dot product with the unit tangent vector along each of these segments. So for instance, along segment 1, and maybe this time I'll write it more explicitly, perhaps if there was any little confusion last time, I'll just make that notation very clear this time again. So for the rectangular loop that we have, the tangential component along segment 1, right? The unit tangent vector along segment 1 is simply pointing along the y direction. So we can say that the tangent vector is just j. The normal to this segment, again, you imagine that you are walking along this segment. So if you were walking along this segment in this direction, the normal will point along the direction of your right hand. So this is the normal along this segment. And so the normal for segment 1 would be along the I direction. The unit normal vector for segment 1 coincides with the unit normal vector along the x direction in the xy coordinate system. Similarly, if you go to segment 2, which is here, the tangent vector is now like this. So it's along minus I. That's the tangent vector. And the normal vector just points in the j direction. When you move on to segment 3, the tangent vector is along minus j, and the normal vector is minus I. And when you move along segment 4, the tangent vector is along I, and the normal vector is minus j. So now, if you want to extract the tangential component of the velocity field for segment 1, all we need to do is take the dot product of the velocity, the velocity vector at the midpoint of the segment with the unit tangent vector, which happens to be the j vector. So from here, if I take the dot product of v1 with j, let's just call this entire thing that we are calculating, since it's again across an infinitesimal loop, let's call this delta C. And I'll just specify why I'm using the symbol C for this case. So just like for flux, we use delta F, let's just call this delta C. So delta C, the first component of delta C, the first component of the flow, so to say, along the tangential direction, along the tangent to segment 1 would be V1, this vector dotted with J. And so that will pick out the component Q x plus del x by 2, comma y. Likewise, you move on to segment 2, and then you take the dot product of the velocity vector at the midpoint there, which is v2, with the tangent along this direction, which happens to be minus I. So that will pick out minus of this component. So we have minus p x comma y plus del y by 2. Along segment 3, we'll take the dot product of this with the tangent along segment 3, which is minus j. And so that will pick out minus q x minus del x by 2, comma y. Similarly, as we move along segment 4, I'll take the dot product of v4, velocity vector along segment 4, with the tangent there, which is the unit tangent vector there, which is I hat. And so that will pick out plus p x comma y minus del y by 2. So just like in the previous video, we'll do a Taylor series expansion. So you see that between these two terms, y is fixed. It's only x which is varying. So if I do a first order Taylor series, oh, by the way, again, just like in the previous video, if you were to now calculate the total flow along the tangent, I'll multiply this by the length of the segment along which we've calculated, because the vector field that we have drawn at the midpoint is just representative. It's a representative vector which tries to capture the fact that the vector field doesn't really change much along the segment, but when I have to calculate the total flow, the field exists at each point, for instance, along the segment. So I multiply by the length of that segment. So if I multiply, so the length, so for the first segment, the length of the segment with which it will multiply is del y, because the length is along the y direction. You're traversing the length along the y direction. For the second segment, it'll be del x. For the third, it'll again be del y, and for the fourth, it'll again be del x. So now I'll take these two terms and I do a Taylor series expansion to first order. So I'll have qx comma y del y plus dou q dou x del x by 2 del y. That's the first order derivative which comes from the Taylor series expansion. Similarly, when I look at this term, I will have minus q x comma y del y plus tau q tau x del x by 2 del y. Likewise, I can do a Taylor series expansion of this term, and I'll pick up p x comma y del x minus tau p tau y del y by 2 del x. And from this term, I'll again pick a negative sign, even though this is a positive. So first order expansion will be positive, but there is a negative term outside. So I'll have minus p x comma y del x minus tau p tau y del y by 2 del x. So we see that these terms just cancel out. Qx comma y cancels qx comma y here. Px comma y cancels px comma y here. And then we are left with these terms and these terms. So these two can be combined together, and this gives us tau q tau x del y, and then minus tau p tau y del x del y, and that's delta c. So delta c, the reason I'm using the symbol c is because the kind of flow we are looking at along or across this loop is the flow which is moving along the tangent to this curve, to this closed path. So one of the ways of thinking about this is it's kind of like the flow is circulating along the segments of this rectangular loop. So C comes from that circulation, and we can call this the net circulation, how much the flow is circulating along the path. So you can imagine maybe making this path using straws and think of how much of the fluid is flowing along the straws as it moves, as it flows along the segments of this rectangular loop, right? So this is called circulation. Or in this case, since it's an infinitesimal loop, we have the symbol delta. So it's infinitesimal circulation. Notice that on the right-hand side, we again have delta A, which is del x del y, which is the infinitesimal area of the rectangular area enclosed by the rectangular loop. So I can divide the circulation. If I divide both sides by del x del y, which is del A, this is kind of like the circulation density. And notice that since we are restricting ourselves to 2 dimensions, the density in this case, is being defined by something divided by area. If you were to do this in 3 dimensions, density is typically defined by some quantity divided by the volume. But since we are in 2 dimensions, we are still calling it a density, but we just have to keep in mind that this is for a 2-dimensional, therefore we divide it by the area. So this is circulation density. Now, what is it that's happening on the right hand side? The circulation density we are claiming is of the form tau q tau x minus tau p tau y. Now, I don't know if you're able to connect the dots here, but if you remember the definition of a curl, and by the way, if you have not yet sort of gone through the course on differential calculus, do visit www.dsigma.in, where we have this introductory course on differential calculus. We introduce the ideas of partial derivatives, divergence, and curl. We derive it from first principles. So hopefully you'll find that useful. So the way we define the curl as the vector which is obtained by taking the cross product of the del operator with some vector field. So in this case, the vector field has 2 components, p and q along the I and j directions, and there is 0 along the k direction. So the way we take the curl is that we have del defined in this manner, the vector del, and then we have p, q, 0. So if you were to define this cross product, you'll see that the only residual terms you will obtain are along the k direction, and the way we write that is that it's along the k direction, and that's tau q tau x minus tau p tau y. So that's the curl of the velocity vector field across sort of the circular loop. And you see that this expression agrees with the one we just derived here. Therefore, what we can say is that the circulation density is equal to the curl of the vector field. Curl of the vector field. So in the previous video, we found that the flux density is equal to the divergence of the vector field. In this case, and we obtained that result by looking at the normal components of the velocity vector field along the rectangular loop, which we have defined for ourselves. Likewise, the circulation density, which is obtained by looking at the tangential components of the vector field, gives us the curl of the vector field. And so that's another interpretation of the curl of a vector field. Now notice one sort of caveat here. The way we've written del C, it looks like it'll be a scalar. Now for 2 dimensions, it won't make much of a difference because the curl that we obtain has just one component which points along the z direction. So for now, we can ignore the vectorial nature of the curl because it's always pointing away, or rather perpendicular to the plane of the flow that we're considering. But in 3-dimensional generalization, we'll have to take care of this. For 2 dimensions, it's okay for now. So hopefully you found this useful. And with this background of having introduced the relation between flux and divergence, and at the same time between circulation and curl, we'll now build this idea further and apply this to a finite region of space in 2 dimensions, for instance, and derive for ourselves what is the generalization of the fundamental theorem of calculus to divergence and curls. So we'll do that in the next part of the video. Thanks for watching.